Okay, I'm going to go ahead and get started. So first off, I want to show you the course website, just so everybody's tracking exactly how the course is going to run from this point on. So my screen should be popping up in a second. Okay, so this is the multi page. So most of what you're interested in is going to be under content. So if you go to content, you'll see a few different things here. So all lectures, if you click, you'll be able to see the detailed notes that Dr. Schmidt is writing up. So he is posting notes for all the different lectures. So you should be able to see those. And those are actually very good. So if you read those, you should get the information you need for the course. And they're relatively short, very digestible. If you look at the revised course calendar, so he posted this as well. So you'll notice that all of the quizzes are listed on Tuesday. So the quizzes are going to be on LMS. So you'll be, Dr. Schmidt will be posting the quiz as an assignment. And then as of right now, I think it looks like we're going to have you guys do the quiz on your own and then upload it as a PDF. So you should be getting guidance shortly from Dr. Schmidt, specifically on the first one because it's coming up. Other than that, all of the lecture notes will be posted. I'll continue doing recitations on Tuesday and Friday. I'll prepare for the quizzes the next week. And I'll also, following the recitations on Friday, I will try to post a video of a recitation. I'll also post my notes, and those will go in the recitation section here. And then I will also post homework solutions. So I solved all of the problems for homework sheet 4 on Saturday. So I'll be able to post those and you'll be able to look at all those solutions. I'll post them up to what's applicable for the quiz the next week so that you can continue working ahead if you so choose. So that's what we're looking at here. So you should be coming back to my notebook. So right now we're starting matrix algebra. So we're shifting gears a little bit from the calculus. In my opinion, this material is much easier to understand than the other material. There is a lot of opportunity for arithmetic mistakes, but the material itself is much simpler as far as kind of the overall concepts. So I'll go ahead and if anybody has any questions on any individual homework problems, let me know. Otherwise, I'll just kind of go through the material chronologically and do homework problems as we go. So to start off, so what is matrix algebra? Camera's generally pretty good, so I wouldn't worry about it. Okay. Every once in a while it'll unfocus. So what is it? So let's say we have, it really pertains to linear equations. So let's write out a linear equation. And what do we mean by a linear equation? So we have an equation right here. And all of the variables are raised to the power of 1. So you'll notice that it's x to the first, x to this first. There's no cosine, no sine, no exponent, no powers. So it's all just linear. So we could solve this one as a line for x1 using point slope. We could do the same thing with the second one. So that's what we mean by linear equations. Now, if we were to take the coefficients in this linear equation, we could pull them out and write them in a matrix. So if we write them as a matrix, this is what's called a coefficient matrix. And if we were to pull out the answers over here, we could form a column vector. So we have a coefficient matrix and a column vector. We could do the same thing with x1 and x2. We can pull them out to make a column vector as well. And typically when we're solving a system of equations, we'll see an equation that looks like this, where the coefficient matrix is A. This is the variables. And then we have the solution is in as B. So that's typically what we'll see. So this is what AX equals B is. when we have a matrix, so the coefficient matrix will often be written in something like this. Where this is an m by n matrix. There are m rows and n columns. And you'll often see Aij written. And when you see Ij, I refers to the row, J refers to the column. So you'll notice that A11, so it's the first row, first column. A12, first row, second column. A21, second row, first column. A22, second row, second column. So that's just some notation to make sure everybody's familiar with. So how do we solve this system of equations? So the way we do it is we use something called an augmented matrix. So an augmented matrix basically pulls these all together. So we end up with something that looks like this. So when you write these and when I write these, it's very useful to put this line right here just to symbolize the separation between the coefficient matrix and the solution. So the coefficient matrix here is a 2 by 2. So we're solving a 2 by 2 system, even though this is a 3 by 2 or a 2 by 3 augmented matrix. And what this means is that these are the coefficients and this is the answer. So that's just a way we write it out. Now, when we have these answers, so let's write this out. So A11 x1 plus A12 x2 equals B1. A21 x1 plus A22 x2 equals B2. So these two equations, you can imagine there's going to be three different types of solutions. So I'm going to go ahead and draw those out. This is x2 and x1. So if we were to plot the solutions to these, so each one of these is going to be a line. So one possibility is that they're both lines and they cross at a single point. So this point right here, x1, x2, would be our solution to this system of equations. And in this case, we would have what's called a unique solution. Another possibility, if we have two lines and they never touch, so they're parallel, then this would be a situation where there is no solution. And the third situation is, let's say we have two lines that are coincidental. They are the same line. In that case, we would have infinite solutions. And then some vocabulary we need. We know that if there is a solution, so if there is a unique solution or there are infinite solutions, we have what's called consistent matrix, so or a consistent system of equations. So there's at least one solution. And then inconsistent system means there's no solution. Okay. Now, how do we solve this augmented matrix? Well, in order to solve the augmented matrix, we use a few tools. So the tools I'll kind of describe briefly. So the way we use this is we make use of what are called elementary row operations. So there are a few things we do with equations all the time, and I'm just put them on the paper so you're familiar with them. So one thing we can do, so if we have 2x1 plus 3x2 equals 4, and negative 2x1 plus x2 equals 4, then we can add these two equations together. And you do that all the time. So we can just take this equation, add it to the other one, and we can get 0 plus 4x2 equals 8. And then from there, we'd be able to solve that system of equations. So this is one tool we can use. That's one elementary row operation. Another one, we can take a row and we can multiply it by a constant. So if we take this equation and we multiply both sides by a half, end up getting x1 plus 3 halves x2 equals 2. So we know we can do that. Nothing complicated there. And then the third thing we can do, which seems very obvious, we have x1 plus x2 equals 3, and x1 plus 2x2 equals 4. Then it doesn't matter. This seems very obvious, but it doesn't matter what order we write those equations in. So if we switch it and we put this equation on top of this equation, it's the exact same system of equations. So those are the elementary row operations. And we're going to use those elementary row operations to get some matrix operations that can help us with solving our problems. So go ahead and flip the page. And if you need to get any notes, just let me know at the end. I can go to those pages. We can go back to them. So the matrix operations. So the first one is, let's say we have a row. We can replace it with any other row. So I and j here just represent any number. So if I have row 1 and row 3, I can switch those rows. So what does that mean? So that means if I have a matrix, so these are coefficient matrices, not augmented matrices, then I can go ahead and write it as 3, 4, 1, 2. And this is the exact same. Or it's an equivalent matrix. It's not the exact same, but it's an equivalent matrix. What else can I do? So I can take a row and I can replace it with a constant times that row. So what does that mean? I can take the same matrix and I can multiply the first row by 2 to get 2, 4, 3, 4. And once again, these are equivalent matrices. And the third thing I can do is I can take a row and I can replace it with a row plus a constant times another row. What does that mean? So that means that I have a matrix. I can take row 2 and subtract 3 times row 1. What does that do? So that gives us, so when I write this, I'm going to write it shorthand. But what I mean here is always that row 2, the first thing I write is being replaced with row 2 minus 3 row 1. So R1 is going to stay the same. And row 2 is going to be minus 3 times row 1. So 3 minus 3 times 1 is 0. 4 minus 3 times 2 is going to be 4 minus 6 is negative 2. So those are the 3 sets of row operations that we're going to use in a little bit. So now that we have those in our arsenal, I'm going to talk about a few things. So there are non-square matrices. So square matrix is what you'll see when you have a solvable linear system of equations with a unique solution. Generally, it doesn't have to be. You could have more columns than rows, but we'll see that. So a few other things that you might see. So you could see a matrix like this. And what does this mean? This means that there are more equations than there are unknowns. So we have 3 equations, and we only have 2 unknowns. So that means that we would be able to solve this in 2 equations. So the third equation would have to be consistent with the first two. In this case, it's actually not. If you were to solve this system of equations, you'd find that this is an inconsistent system. However, if we were to have more columns than rows, then you can see that there are more unknowns than our equations. So we have 2 equations and 3 unknowns. So since there are more unknowns than equations, there's no way we can solve for 3 unknowns with only 2 equations. So in this case, we're going to have what's called a free variable, which we'll talk about in a little bit. And it basically means that if there are more unknowns than equations, then there will be infinite solutions. Okay. So if we have an augmented matrix and we want to solve the system, the first thing that we're going to have to do is get it into what's called echelon form. So what is echelon form? So there are a few rules to get echelon form. The first, all 0 rows are at the bottom. So if there's a row with only zeros in it, then it'll go at the bottom of the matrix. The second rule, so the leftmost non-zero entry is 1. And then our third rule is that the leading 0 is farther right in row I plus 1 than in I. So we can see farther right in row 2 than row 1, row 3 than row 2, etc. So what does this look like? So here are a few examples. First one. So this is a coefficient matrix, and we can see that there are no 0 rows, but the leftmost non-zero entry in every row is 1, 1, 1, 1, and the leading 0 is farther right in row I plus 1 than in I. So in row 3, the leading 0 is farther right than in row 2. So this is in echelon form. Another example. So in this matrix, there are no 0 rows again, but we can see that the leading entry is a 1 in each row, and the leading 0 is farther right, so there's only a 0 in the second row. In the third example, so once again, so we have a 0 row, and it's at the bottom. The leftmost non-zero entry is 1 in each row, and the leading 0 is farther right in row 3 than in row 2. So this is also in echelon form. So then the next step when we're doing solving the system is we want to get it into what's called reduced echelon form. In a reduced echelon form, it has one more rule. So in this rule, it says each leading 1 is the only non-zero entry in that column. Okay, so if we have reduced echelon form, here are a few examples. So in the book, one of the homework problems is to say whether matrix is in reduced echelon or not. So I'm going to show a few that are in reduced echelon. So if we have a 3 by 3 matrix, we can see that this is in reduced echelon. So it follows the rules, the first 3 rules, and then the leading 1 is the only non-zero entry in that column. So there's only the leading 1 is the only non-zero entry in each of these columns. Another example. From above, we can see that not only is this in echelon form, but this is also in reduced echelon form. So we have 1, 0. The 1 is the only non-zero element in that row. A third example, let's say we have more rows than columns, and we'll get something that looks like this. So this is in reduced echelon form. It follows the rules for the first 3, and then 1 is the only non-zero entry in each column. Okay. And why is it useful to get it into reduced echelon form? Here's why. So if we have an augmented matrix, then if it's in reduced echelon form, it'll look like this. So let's say we have 1, 0, 0, 0, 1, 0, 0, 0, 1, 3, 4, 6. And what this means is that x1 equals 3, x2 equals 4, and x3 equals 6. So if we can get the matrix into reduced echelon form, then we have the solution to our matrix, and we're good to go. We have everything done. Okay, so now we're going to do a few examples. So we'll do a few examples of Gaussian elimination to give you a little bit of a view of the process. So when we're doing Gaussian elimination, these are all homework problems from here on out. So first example, let's say we have the matrix 0, 2, 0, 0, 2, 1, 3, 4. Okay. So what is this? So this is equivalent to 2x3 equals 3 and 2x1 plus x3 equals 4. So we can solve this pretty easily, and we get that x3 equals 3 halves, and x1 equals 1 half and 5 fourths. So we should get this solution when we do our Gaussian elimination. So now let's try it with Gaussian elimination. So in order to get it into echelon form, we're going to need a 1 in the upper left. So we're going to have to switch these rows. So the first thing we're going to do is we're going to take row 1 and switch it with row 2. And that will give us this matrix. So you can see all I did was switch these 2 rows. Now the next thing we need to do, in order to get echelon form, we need to have a 1 in the upper left. So in order to do that, we're going to take 1 half times row 1. That'll give us, the bottom will stay the same, and the top will be 1 half. So 1 half times 2 is 1, 0, 1 half, 2. Now, in order to get it into echelon form, we need this leading entry to be a 1. So the next step we're going to do is we're going to take 1 half times row 2. And row 1 will stay the same. Row 2 will become, sorry, 2, 1, 3 halves. And now the last thing we need to do, so this is in echelon form now, but we have to get it into reduced echelon form. So what we're going to do is we're going to take row 1 and we're going to subtract 1 half times row 2. So row 1 minus 1 half row 2. And that's going to keep row 2 the same. And the first row, 1 minus 0 is 0, 0. 1 half minus 1 half times 1 is 0. And 2 minus 1 half times 3 halves is 2 minus 3 quarters, which will give us 5 quarters. So notice x1 equals 5 fourths, x3 equals 3 halves, and now x2 is just multiplied by 0 in each case. So x2 is what's called a free variable. And what that means is we can choose whatever we want for x2, and it'll still be a solution to the problem. So let's go ahead and look here. So some solutions to this problem. So we could choose 5/4, 2, 3/2, because the second one doesn't matter. We could also choose 5/4, 1,000, 3/2. So it doesn't matter what we choose for this free variable, it will still be a solution. Okay, so now let's look at another example. So this one's a little bit different. So let's say we have the matrix 1, 2, 1, 0. Okay, so there's our matrix. So this is actually already in echelon form. And now we have to get it into reduced echelon form. So let's take this matrix, and what do we have to do? We have to get rid of this so that we have only non-zero entry in this column is this 1. So we're going to do row 1 minus 2 row 2. And that will give us row 2 will stay the same. And we're doing 2 minus 2 times 1 is 0. 1 minus 2 times 3 is going to be negative 5. 0 minus 2 times 1 is negative 2. Now this is in reduced echelon form. So if we write these out, it's x1 minus 5x3 equals negative 2. And x2 plus 3x3 equals 1. So another way to write this is if we write x1 equals negative 2 plus 5x3, x2 equals 1 minus 3x3, and x3 equals x3. So x3 is what's called a free variable. So x3 does not depend on anybody else. We can choose whatever x3 value we want, and it's not impacted by anybody else. X1 and x2 depend on x3. So they're what's called constrained variables. So we can see that what we choose for x3 will affect what our x1 and x2 are. So some solutions. So if we were to choose x3 equals to 0, then one solution would be negative 2 plus 0, so we get negative 2, 1, 0. So that's one solution. Another solution, let's say we choose x3 equals 1. Then we would have negative 2 plus 5 is 3, and 1 minus 3 is negative 2. So we can see that each of these is going to be a solution to this problem, and we can literally choose any value we want for x3, and it will still be a solution for this system of equations. So that's what happens when we have dependent variables in the end. A third example, so let's look at one where you have an n by n matrix. So this is a 2 by 2 coefficient matrix. So to get it to echelon form, we're going to have to divide the top row by half. We do 1/2 row 1. That will give us 1, 2, 3. The bottom row will stay the same. And then we can add these together. So if we want to get rid of this negative 1 down here, so in order to do that, we can add row 1 to row 2. That's row 1. So our row 1 will stay the same. And negative 1 plus 1 is 0. 4 plus 2 is 6. 12 plus 3 is 15. And now we need the leading 1 in every row to be 1. So we're going to go ahead and divide this by 6. 6 times row 2. That will give us 1/6 times 6 is 1. 1/6 times 15 is 5/2. And now the last thing we need to do is we need to get rid of this 2 so that 1, the leading 1, is the only non-zero entry in its column. So in order to do that, row 1 minus 2 row 2. The bottom row remains the same. And the top row becomes 2 minus 2 times 1. 3 minus 2 times 5/4 will give us 3 minus 5, which is -2. So what does this mean? This means that x1 equals -2 and x2 equals 5/2. So we've solved that system of equations. Okay. The last thing that I wanted to make sure I got into is a little bit more complicated example. So I'm going to go over one more example, and this one's a little bit more complex. So let's look at our system of equations. So let's say we have x1 plus x3 plus x4 minus 2x5 equals 1. Okay, so there's our system of equations. So the first thing we want to do is write out the augmented matrix. So if we write it out, we end up getting in the first column 1, 2, 3. Second column 0, 1, -1. Third column will be 1, 3, 4. Fourth column will be 1, -1, 1. Fifth column will be -2, 1, 1. And then we have our solution is 1, 0, 1. So that's our augmented matrix. So we need to get this augmented matrix and we need to transform it into reduced echelon form. So in order to do that, we need to make sure that this leading 1 is the only non-zero entry in this column. So we're going to have to subtract row 1 from rows 2 and 3 to get rid of the 2 and 3. So the first thing we'll do is we'll take row 2 minus 2 row 1. And that's going to give us, so since all we're changing is row 2, row 1 and row 3 will stay the same. I'm going to go ahead and write those out. So we're going to get 2 minus 2, 1 minus 0, 3 minus 2, -1 minus 2. 1 minus 2 times -2 is 1 plus 4. So we'll have 5. And 0 minus 2. So we do the same thing with row 3. And we subtract 3 times row 1. So rows 1 and 2 are going to stay the same. And row 3, so 3 minus 3 times 1 is 0. -1 minus 0 is 0. I miswrote. Sorry. This guy's a 1. Okay. 4 minus 3, 1. -1 minus 3 is going to be -2. 1 minus 3 times -2 is going to be 1 plus 6. It's going to be 7. 1 minus 3 is going to be -2. Okay, so now we have our updated matrix right here. And in order to get it into reduced echelon form, or into echelon form, we're going to have to make sure that this is the only non-zero entry, and it's that the leading one is that there's no value below it. So we're going to have to get rid of this -1. So how do we do that? Let's go ahead and add row 2 to row 3. Row 3 plus row 2. So row 1 and row 2 are going to stay the same. And then for row 3, we're going to get 0. We get 1 plus -1 is 0. 1 plus 1 is 2. -2 minus 3 is -5. 7 plus 5 is 12. And -2 minus 2 is -4. Now, in order to get echelon form, we need a 1 down here. So let's go ahead and take row 3. We'll divide it by 2. And that will keep row 1 and 2 the same. And row 3 will become 1, -5 halves, 6, and -2. Okay, so now we have the matrix and it's in echelon form. Now the next step we need to do is get it into reduced echelon form. So in order to do that, we're going to have to subtract row 3 from row 2 and row 1. So let's start with row 1. So we'll do row 1 minus row 3. So row 2 and 3 are going to stay the same. And our top row becomes 1, 0, 1 minus 1, 0, 1 minus -5 halves is going to be 1 plus 5 halves. 7 halves. -2 minus 6 is going to be -8. And 1 minus -2 is going to be 3. Now the last step is we're going to take row 2 minus row 3. So row 1 is going to be, row 1 and row 3 are going to stay the same. Row 2, 1 minus 0, 1 minus 1 is 0. -3 minus -5 halves is going to be -1 half. 5 minus 6 is going to be -1. -2 minus -2 is 0. So now we have our matrix in a form that we can get a solution from. So if we were to write this out, you see that x1 plus 7 halves x4 minus 8x5 equals 3. x2 minus 1/2 x4 minus x5 equals 0. And x3 minus 5 halves x4 plus 6x5 equals -2. And if we were to rewrite this, we can write it as x1 equals 3 minus 7 halves x4 plus 8x5. x2 equals 1/2 x4 plus x5. x3 equals 5 halves x4 minus 6x5 plus or minus 2. Okay, so there's our list of equations, and then we have x4 equals x4, x5 equals x5. So x4 and x5 are our free variables. We can choose whatever we want for those guys. And then x1, x2, and x3 are constrained. Because we can choose whatever we want for those. So we could choose 1 and 2, we could choose negative 546 and 23. And if we plug those in here, the solution would be a solution to this equation up here. So that's kind of the process. So this process that we've just gone through is called Gaussian or Gauss-Jordan elimination. And basically we go through the whole process and it gives us our solution. It'll either give us a unique solution or it will give us an infinite solution, or let's look at an example. So if we get what does an inconsistent system look like? So let's say we were to do all of our matrix operations and we end up getting something that looks like this. And what this means is, if you look at the bottom row, we have 0x1 plus 0x2 plus 0x3 equals 4. So this is inconsistent. And then if we were to have something that looks like this, this is consistent. As we can see, 0 equals 0. So, oh, sorry. So we can see that this one's inconsistent because we have 0x1 plus 0x2 plus 0x3 equals 4. So 0 equals 4. There's no solution to this problem. Over here, if the bottom row is all zeros, then it can still be a consistent system. So that's kind of the difference. So when we do our Gauss-Jordan elimination, we had one example where we found a unique solution. This example right here is one where we found a infinite solution. So we have two dependent variables. And then down here, we have an inconsistent system. And that's when we do the Gauss-Jordan elimination. If we run into something like this, that's a no-go. It's not going to work. Does anybody have any questions on this process or anything at all in the lectures or the notes so far? Or any other homework problems you wanted me to go over?
Yes, sir.
Yes.
Could you do the section 1.2, the practice one?
1.2 from the lectures?
I think our homework.
Okay, so 1.2.
Section 1.2 and the practice 1.2.
Practice 1.2. Okay, let me go through here. Do you know what page it's on?
It doesn't have the page. Professor just copied it on our homework.
Oh, okay, from the homework itself. Okay, yeah, let me pull that up.
It's like the third row, I solved it as 0, 0, and 37. So I was a little bit confused.
Oh, number 2. So the 2x2 matrix A and B.
No, it should be 3x3 matrix.
So practice problem number 1. The one that says reduce the following matrix to reduced echelon form.
Yeah.
Without introducing any fractions. Okay, so yeah, I can do that real quick. So let's look at our matrix. So let me okay, so this one's a little bit long, so we might go a little over time, but so we have a matrix, so looks like this: 2, 0, 3, 1, negative 2, 4, 3, 7, 5. And we're supposed to get this to reduced echelon form without introducing any fractions. So without introducing any fractions, there are a few different ways we can do this. So we need to get a 1 up here. So you can see if we divide this row by 2, we'll have 3 halves, which will be a fraction, and 1/2 will be a fraction, so we can't do that. What we can do is if we take row 1 and we subtract row 3. Let's do row 1 minus row 3. And that'll give us row 2 and 3 will stay the same. And row 1 will become 2 minus 3 is -1, 1 minus 4 is -3, and 3 minus 5 is -2. So then if we were to go one more time, we almost have it. So now let's multiply this top row by -1. And there are an infinite number of ways to do this. This is just one way. But if we were to do that, we can get the top row be 1, 3, 2. And the bottom 2 rows will stay the same. So now we have the top as 1. So in order to get it to echelon form, we need to get rid of this 3. So if we take row 3 minus 3 row 1, that'll get rid of that 3. So row 3 minus 3 row 1. So row 1 and 2 will stay the same. And then row 3 will become 0. So 3 minus 3. 4 minus 3 times 3 is 4 minus 9, which will give us -5. And 5 minus 3 times 2 is going to be -1. So now, once again, we can't divide by 2 here, -2 here, and we can't divide by -5 here. Because then we would get something that doesn't look right. But what we can do is we want to get a 1 in one of these two spots. So we can see that if we subtract 2 times row 2 from row 3, this will become -1. So let's do that. So let's do row 3 minus 2 row 2. And that will give us row 1 and row 2 will stay the same. And the bottom row will get -5 plus 4, -1. -1 minus 14 will give us -15. Now, let's go ahead and switch these rows so we get the 1 in the right spot in the matrix for echelon form. So let's switch row 2 and row 3. And row 1 will stay the same. Row 2 will become that, and row 3 will become this. And now, in order to get the 1 in the second row, now let's multiply the second row by -1. And row 1 and 3 will stay the same. Okay, so we're almost there. We're almost at echelon form. So let's go ahead and get rid of this 2. In order to do that, we're going to have to add 2 times row 2 to row 3. So row 3 plus 2 row 2. And that's going to give us row 1 is going to stay the same, row 2 is going to stay the same, and row 3 plus 2 row 2 is going to end up being 0, 0, and then 7 plus 2 times 15 is going to be 37. And now, in order to get this bottom one, in order to get a 1 in the lower right position, we're going to divide the bottom row by 1 over 37. So we're going to get 1 over 37 row 3. And that'll give us our matrix in echelon form. And now, nice and easy. So let's go ahead and get rid of the remainder. So to get rid of the 3, let's do row 1 minus 3 row 2. And that will give us 2 and 3 will stay the same. 1, 0, and then 2 minus 3 times 15 will give us negative 43. And then from here, all we're doing is adding row 1 plus 43, row 3. And now row 2 minus 15, row 3. And that'll give us our matrix in reduced echelon form. And you notice over the entire process, we didn't introduce any fractions. We had to take a lot more steps because we didn't want to get any fractions, but we were able to get to the solution. Does that make sense?
Yeah.
Okay.
So is that include the answer already? I mean, like.
No, so this is just a matrix. This is not an augmented matrix.
Oh, okay. Okay, sure.
So the answer is not part of this.
Oh, yeah. Thank you.
Okay. Did anybody else have any questions? Okay, if not, go ahead and have a great weekend. Hopefully, Dr. Schmidt will post the quiz information for you soon. Just know that will be on Tuesday, that will be due on LMS. Okay, have a great weekend.
Thank you.